Consider the voltage regulator circuit in the figure on your screen. A string of 3 diodes is used to provide a constant voltage of about 2.1 volts. We want to calculate the percentage change in this regulated voltage caused by A plus minus 10% change in the power supply voltage, and B, a connection of a 1 kilo ohm load resistance. Assume N equals 2. Now for our solution, first we find the current value at DC. This is 7.9 milliamperes. Each diode will have an incremental resistance of 6.3 ohms. Since they are in series, the total resistance will be 18.9 ohms. This resistance, along with the resistance capital R, forms a voltage divider whose ratio can be used to calculate the change in output voltage due to a plus minus 10% change in supply voltage. The plus minus 10% change can also be written as a plus minus 1 volt change in supply voltage. Thus, the peak-to-peak change in output voltage will be 37.1 millivolts. The 2 over here is because we are considering peak-to-peak voltage. In other words, plus minus 1 volt can also be written as 2 volts peak. The percentage change in the output is approximately 0.9%. Notice that we have used 18.5 over here, whereas we had 37.1 millivolts over here. The reason is that 37.1 millivolt was a peak-to-peak voltage and 18.5 milli is simply the amplitude. Therefore, we are going to use 18.5 in the equation. An 18.5 millivolts change in the output implies a change of about plus minus 6.2 millivolt in each diode. So, this is a very small voltage and our use of the small signal model is justified. Now coming to the next part. Now when a load resistance of 1 kilo ohm is connected across the diodes, as you can see on the right side of your screen, the load resistance draws a current of approximately 2.1 milliampere. Why? Because we have employed this equation and the current comes out to be 2.1 milliampere. However, the current in the diodes decreases by 2.1 milliampere as a result. So, the decrease in voltage across the diodes can be given by this equation and the value comes out to be minus 39.7 millivolts. This is slightly larger than the 37.1 millivolts that we had calculated in part A, albeit for different conditions. However, this time the voltage change across each diode is minus 13.2 millivolts, and so our use of the small signal model is not entirely justified. However, if you make a detailed calculation using the exponential model, our change in voltage results in minus 35.5 millivolts, which is not too different from the calculated voltage using the small signal model, that is minus 39.7 millivolts. The percentage change in the regulated voltage V0 for this part comes out to be minus 1.9%, which is higher than that calculated for part A. I hope these two exercises gave you ample practice for the small signal model. You should try this one too yourself.